In section 5.3, we're taking the concept of a base of a vector space and we're honing in on it and making it a lot easier to use. What we're going to do is we're going to take a given basis and we're going to manipulate those vectors. Remember, a basis will, any linear combination of the vectors in a base will produce every single vector in the space. So because that's true, we can come up with different vectors in that space that also form a basis and make sure that those vectors are perpendicular to each other. Even in n-dimensional space, this can be done. And then if we take that new base set of vectors and we normalize them, which means making them 1 unit each, then we've got a very useful set of vectors that will span an entire vector space. So here we go. First off, section 2 that we skipped is about inner product spaces. What an inner product space is just a vector space like we have studied before, where it's closed under vector addition and scalar multiplication, but we've added a definition of something called an inner product. Now in the real space, n-dimensional real space, that inner product that's normally used is just the dot product, which we've studied. So you'll see in the homework that in other types of spaces like polynomials or continuous functions or things, they may give you a different definition of the inner product for that particular space. We'll focus almost exclusively, though, on the regular dot product. The book uses notation for an inner product that I was always taught was the notation for a vector itself. If you see, and I did this earlier when we studied vectors, I used the pointy things. In this book, when the two vectors are listed inside the pointy things, that means it's the inner product of those two things. Inner product. All right, so it can cause some confusion. They usually list the components of their vectors just in plain old parentheses, which can make it look like a point. But if you think of every vector as, you can move a vector around, right? And it maintains its direction and magnitude. You just think of every vector as being initial point at the origin, and the terminal point is the numbers in the parentheses. So if we think of it that way, then we won't get confused. All right, so getting that definition of an inner product space, when you read that in the homework, just understand it's a vector space like you've been dealing with all along. And because we're going to be focused mostly in the real space, we're just going to use a plain old dot product that we're comfortable using and we've gotten used to. Okay, orthogonal sets of vectors. Every vector in an orthogonal set is orthogonal to all the other vectors in the set. Remember, to show that two vectors are orthogonal, it just means that the dot product is 0, right? Because the angle between the vectors is pi over 2, 90 degrees, and the cosine of pi over 2 is 0. So orthonormal is when we take that orthogonal set and we normalize every vector in the set. In other words, we find its magnitude, and 1 over the magnitude is the scalar multiple, and we get magnitude of 1 for each of those vectors. Theorem 5.10, orthogonal sets are linearly independent. That's very important because it leads to the corollary that comes next. So if all of your vectors are linearly independent, think about that. None of them are scalar multiples of the other, and none of them are linear combinations of another because they're all perpendicular to each other, right? Okay, so the corollary, if V is an inner product space of dimension n, in other words, the dimension is known, any orthogonal set of n non-zero vectors is an orthogonal basis of the vector space or the inner product space. Remember, orthogonal sets are linearly independent, and if the dimension is known, theorem 4.12 said that if the dimension is known, you only have to satisfy spanning or linear independence. So if either one of those is true and they're orthogonal, which means one of them is true, then that means it is a basis. So if you're in third dimensional space and you have three vectors that are orthogonal to each other, you can know that you have an orthogonal basis. Okay, finding an orthonormal basis from a given basis, first you have to find new vectors from the beginning basis that are all orthogonal to each other. Once you get those vectors, you're going to normalize them, and we have a process for doing that, which comes next. This is a snapshot of something in your book. I just wanted to explain some of the bits because holy crap, look at this. This is horrible, isn't it? But let's look at the notation. Projection of one vector onto another. Remember that if I'm projecting this vector right here onto another vector, think in terms of this vector being the screen, the movie screen, and the projector is perpendicular to it, and you shine the light. Let me do some yellow lines to show where the light goes. You're shining the light this way, perpendicular to the screen, and then this blue vector here is the shadow of V2 that lies along V1. So the projection of this vector onto this vector gives you this smaller vector. See how this vector is in the direction of V1, but you're getting the component of V2 that's in the direction of this other. Now, we can take any vector and break it down into horizontal and vertical components, right? And the sum of those two vectors is your vector. This is the same thing, it's just that it's twisted away from the XY axes. Do you see that? We just twisted it up. So now we're just changing the coordinate base is what we're doing. But remember what a projection is. The projection is the dot product of two things divided by the magnitude squared times the vector that you're projecting onto. This gives me direction divided by the magnitude one time gives me a unit vector in the direction of W1. This magnitude, because this will be magnitude squared under here, remember what you get when you dot a vector with itself, you get magnitude squared. This magnitude right here cancels out the magnitude that's in the dot product, because the dot product is magnitude, cosine of the angle, right? So one of the magnitudes is canceled, and you're left with a magnitude of V2 times the cosine of the angle between V2 and W1. See, we just take W1 to be the first vector in our basis. So now we're, this piece right here is going to be this projection right here subtracted from that vector. When you subtract vectors, V2 minus this projection, you go from the tip to the back to the tip, and you're going to get this vector right here, which you can see is perpendicular to your first vector v1 or w1 now. So now you have two vectors in your basis that are orthogonal to each other, and you keep doing the same kind of process over and over again to get as many vectors as you need for your basis and whatever you need. And you need n vectors to be in your basis if you're in n-dimensional space, right? So the third vector will be the third vector in your original basis minus the third vector dotted with the first divided by blah, 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 right? So the only difference between this and what you did before is you're taking that third vector and dotting it with your original. You can think of the very first vector as being the basis of your basis almost, or the anchor of your basis. So again, you're finding a component that's projected onto U1. But remember, once you get to W3, you're in three-dimensional space. So it's kind of like X, Y, and Z. You've got three dimensions. If you stick out your first finger and then your middle finger perpendicular to your first finger, and then you stick your thumb straight up in the air, you see how you have three orthogonal vectors, or the X, Y, and Z axes. They form an orthogonal basis for three-dimensional space. The second one, you do the same thing, but now you've got your V3 because you're working on W3, and it's dotted with the vector that you just found in the previous step, the magnitude squared underneath, projected onto that second vector, and you're subtracting as you go to get that three-dimensional thing. And as you're in upper level in space, you're finding them that way. It can get pretty nasty, by the way. Okay, for example, this is number 28 in your book. Let's say we're in R2 and we have these two vectors that form a basis for R2. You can check them if you want. If you find the dot product of this and this, you'll see that it is not orthogonal. They are not orthogonal to each other. They are also not normal. Their magnitudes are not 1. So we're going to start by setting our first vector equal to our first vector. Then the second vector is going to be the first vector minus, here we go. This right here is the dot product of the first and the second, which we get as 6. This right here is the magnitude of the first vector squared, and that's multiplied by the first vector. So you're going to just get a common denominator and do the subtraction. You get all of this nastiness, and look at that awful looking vector right there. But don't panic, it's all right. You can factor out the 1 over 25 if you want. There's also common factors between 51 and 68, which we'll see in just a second. Okay, so this is my second vector, and I only need 2 to make a basis in R2. But this vector and this vector are not normal. They're orthogonal to each other, and you can do the dot product of this vector and show that it equals 0, which means they're orthogonal, but they are not orthonormal. You still have to divide each of them by their magnitudes. So we showed right here the magnitude of W1 is 5. So 4/5 and -3/5 gives me my normal first vector. And taking this W2, square it, add them together, and then take the square root of the sum. You're going to reduce your fraction. You're going to get 17 over 5. Now, taking this vector and dividing by 17/5, 17 will divide into the 51 and the 68, and you'll see that you get this nice, neat vector. Check it. What's the magnitude of this? Square it, add them together. Make sure that your magnitude is now 1, and you can do the same thing for this. Check it, and you see this forms an orthogonal basis for all of two-dimensional real space. Another thing that you're asked to do in this section is to find a coordinate matrix. This is just going to be a column vector relative to an orthonormal basis that's given. So you're going to, you're given this vector and you're given this basis. What you're actually doing is rewriting your vector W as a linear combination of this basis. So because every single vector in R4 can be written as a linear combination of this basis, and by the way, it's orthogonal and it's normal. So any dot product of any two of these is going to be 0, and the magnitude of any of these is 1. And you can check it. It might be beneficial just to get in the habit of always checking. It's simple to do. You can do it in your head probably. So here we have this orthonormal basis. Every vector in R4 can be written as a linear combination of these 4 vectors. We want you to do that to create W, okay? So there's a particular way to do this. Now remember, the magnitude of all of these vectors is 1. So if you find the projection of W onto any one of these vectors, then let me just very quickly write the projection. Projection of W onto V, 1 to whatever, whichever one it is the dot product. Sorry, yeah, okay, that's the notation that they, yeah, no. I'm going to use my own notation just to keep it. W dotted with V divided by the magnitude of what I'm projecting onto squared in the direction of the V. Now, one more time, we've done this before. W dot V is the magnitude of W, magnitude of V, cosine of the angle between them, and the bottom is magnitude times magnitude, and this is all times the vector V. Well, you see, this cancels this, and if I take this guy and put it over there, now I have a unit vector in the direction of V. That leaves me with this guy and this guy. Well, if you, this is the hypotenuse times the cosine, which leaves me with just the adjacent. So what you're looking at is a unit vector in the direction of V times the shadow, the length of the shadow of W in that direction. So you get a new vector that is the right length and it's in the right direction. So that's the process that is happening here. But this dot product right here and that vector right there, remember V is part of the orthonormal basis, that this is 1. This is already a unit vector. This is already a 1. So all we're doing is finding the component of W that's in the V direction, and we're going to do that for V, every single one of these vectors, and we'll come up with the vector W written as the linear combination of each of these vectors. So let me clear my space and we will work the problem here. So I'm going to find W as the dot product of 2 minus 1, 4, 3 with, and this is, again, I'm mixing up notation. You don't care, do you? Dotted with the first vector, 5 over 13, 0, 12 over 13, 0. And that's going to be, that's just a scalar right there. So that's a number, and we're going to multiply that by the vector itself. And I'm not going to write this out for the rest of them. I'll just do the algebra in my head, or the arithmetic, plus continue on. So let's see what we have here. This dot product, I'll do this in blue below so we can see it. 2 times 5/13, negative 1 times 0, 4 times 12/13, plus 3 times 0, and this is going to give me 58/13. So that's my first component of W, is going to be 58/13 times 5/13, 0, 12/13, 0. Next, we have the dot product of W and 0, 1, 0, 0. That's a scalar, times the vector 0, 1, 0, 0. Okay, the dot product of W and that vector is just going to give me -1. All right, next we have W dotted with the third vector here. So we're going to get -24/13 plus 20/13, and that's going to give me -24 plus 20 is -4/13 times that third vector. These are ugly, aren't they? It's all right. We don't actually care about the vector. We just need those coefficients. All right, plus the dot product of W with the third vector, and you see that that's just a 3, so it's +3 times that third vector. Now, the directions didn't say find the vector, it said find the coordinate matrix. And what that means is these things that are multiplying the basis vectors, the numbers, the coefficients of the original vector, right? Because W is our coefficient matrix. I'm going to call it A, just for kicks, times B, right? And I did that backwards, so it's from the way the book tells me to do it. So we have the basis, sorry I can't find my pen, we have the basis times the coordinate matrix, and A is, the basis is going to be a 4x4 matrix, and we're going to multiply that by a 1x4 matrix, and that 1x4 is those coefficients that we found, which are just the dot products. So this is actually a very simple process. You're just going to find the dot product of each of these basis vectors with your vector that you're rewriting, and those are going to be the coordinates of that you're multiplying this basis by to get that linear combination. If you want to work it out, multiply these guys out and see that you're going to get what you're looking for. You're going to take all of the x's, add them together, and you'll see that you get 2. Okay, in this problem, we're given a basis for R4, and we want to use the Gram-Schmidt process to transform this into not just an orthogonal basis, but an orthonormal basis. So the first step is to find 4 vectors from these vectors that are orthogonal to each other, okay? So we're going to refer back to the other page that had that process on it. Step 1, we set our first vector, I'm going to call it W1, equal to our first vector. Oh, by the way, the directions for these problems in the book say use the order that's given. If you put these basis vectors in a different order, you're going to come up with a different orthogonal set. So if I was doing it just for me, I would pick an easier vector to start with, but it really doesn't matter. I mean, the magnitude of this vector is square root of 2. Same thing here. Whereas the magnitude of this vector is 5. And it gets a little hairy because you're going to have lots of denominators with 25 in it, which is 5 squared, instead of a denominator with 4 in it for either one of these. But it's still doable. It's not a big deal. So we're going to get going. U1 equals the original. W2 is V2 minus 1, 1, 0, 0, minus, here's where it gets fun. We're going to find the dot product of those first two vectors. So let me write this out here. 3, 4, 0, 0, dotted with minus 1, 1, 0, 0, divided by the magnitude of W1 squared. So we kind of don't need that square root, right? So 3 squared plus 4 squared is the magnitude. So on the bottom, I have 25. The magnitude of W1 is 5. So magnitude squared is 25. On the top, we get minus 3 plus 4, plain old 1. And that is times the first vector. All right, let's see what we got here. Minus 1, 1, 0, 0. Subtract 1 times the original vector divided by 25. I'm going to have to get a common denominator. So this is going to give me negative 25 minus 3 is negative 28, 25. Next is 1, which is 25 over 25, minus 4, which gives me 21. 0 and a 0. So that's my second vector. I'm going to have to find the magnitude of this. So I'm going to keep track of my magnitudes over here on the side. The magnitude of W, we'll need them when we're normalizing. Magnitude of W1 is the square root of 9 plus 16 square root of 25. All right? The magnitude of W2, it's a little bit messier, equals, I'm going to square each of them and then take the square root. After I add, I'm going to take the square root. So I know that 25 squared under the square root is 25. So I need to square 28, square 21, add them together, and I'm going to get 28, squared plus 21 squared is 1225. Square root that, I get 35. That's the magnitude of W2. And this is reducible, 7 over 5. All right, so let's keep going. We've got 3 of these things to find. W3 equals the third vector in my basis, which is 2, 1, 0, minus 1, minus the dot product of this vector and the first vector in my basis, which is going to give me 2 times 3, 1 times 4, 0 times 0, 0, 0, 0, 0. So that's a 10 over the magnitude squared of the first vector times the first vector minus the dot product of my current vector with the vector I just found. Now this is kind of gross, but hang with me here. Dot product 2 times negative 28 is negative 56. 1 times 21, 0 times 0, 0, 0, 0, 0, 0. That's the dot product over the magnitude of W2 squared is 49 over 25. Some 25s are going to cancel, times that vector. And we're going to reduce this puppy down quite a bit. All right, so go back to my blue so I can do some cheating here. This is a 10. Cancel, cancel, and I can reduce that to something a little bit more useful. Now, when I add right here, I've got 25 in my denominator. Negative 56 plus 21 is going to give me negative 35 over 25. Now let's look and see what happens here. The guy on the bottom flips. The 25s will cancel. 49 and 35 are both multiples of 7. So this gives me a 7 on the bottom and a 5 on the top. Negative, right? But minus a negative is a plus. So I've got 5/7 to distribute through this. Well, the 5 on the top is going to cancel with the bottom, and both of these numbers on the top are divisible by 7. So this vector simplifies down very nicely, kind of, sort of. I have 2, 1, 0, negative 1, minus 6/5, 8/5, 0, 0, plus this last one. Remember, the 5 on the top cancels the 5 on the bottom. I get 5 on the bottom, and 7 goes into 28 negative 4 times. 5 cancels with a 25. 7 goes into 21 3 times. 0, 0. So when I subtract, I have 10/5 minus 6/5 is 4/5. Minus 4/5 gives me a beautiful 0. Next, 5/5 minus 8/5 is negative 3/5, plus 3/5 gives me a 0. Then I have 0 minus 0 plus 0. Oh, gotta love it, right? Last, I have negative 1 minus nothing, and that gives me negative 1. So W3 is already normalized, and it's very pretty, isn't it? One more, W4. W4 is the last vector in my basis, minus the dot product of this vector with my first, which is just going to give me a beautiful 4, divided by the magnitude of the first squared times the first, minus the dot product of this guy with this ugly guy right here that I found. So when I dot that, I'm going to get 21 over 25 and zeros everywhere else. So I get 1 times 21 over 25 divided by the magnitude of this vector. Where is it? This vector right here. And we found that to be 7/5. So the magnitude squared is 49 over 25. See, the 25s are going to cancel. 49 and 21 are going to reduce. Hold on. And that's times that ugly vector there. Minus 28 over 25. 21 over 25. 0, 0. And now the last bit is my vector here, the dotted with W3. You see that when I dot this with this, I get a 0, minus nothing. All right, so cleaning up a little bit, 25s will cancel, the 3 here, the 7 here. But when we distribute 3/7, the 7 goes into the top numbers and it makes it really pretty. So I'm going to rewrite what I've got here. W4 equals 0, 1, 1, 0 minus 12 over 25, 16 over 25, 0, 0, minus, distributing the 3/7 is going to give me, 7 goes into negative 28, negative 4 times the 3 over the 25, and I'm running out of room. The second one, 7 goes into 21 3 times 3. Sorry, I get a 9 over 25 and a 0 and a 0 minus nothing. And W4 is going to be 0 minus 12/25 plus 12/25. Booyah. Next, 1, which will be 25/25, minus 16, minus 9, 16 and 9 is 25, boom. Third, I have a 1 here, minus 0, minus 0, minus 0, and I get a 0. The last number is, sorry, I made a mistake. Look at me, look at me, look at me. I caught myself because I was going to get 4 zeros and I knew that couldn't happen. And it's kind of important to be able to catch yourself in a mistake too, because you understand what's going on. 1 minus 0 minus 0 minus 0 gives me a 1. And then the last 4, all 4 of them are zeros. So your orthogonal basis is now these vectors. But we have to normalize them. So what we have to do is take each of the vectors and divide by their magnitude. Well, the magnitude of this is 1, magnitude of this is 1. The magnitude of this is 7/5. So we're going to distribute 7/5 through this vector right here. Let me write what that equals. This is W2. And this is W1 at the top, okay? So my unit vectors that form an orthonormal basis, is U1 is the vector 3, 4, 0, 0 divided by the magnitude of the vector. Vector 2 is nasty, right? These numbers right here divided by 7/5. So if I divide by 7, I get -4 in the top, and I'm flipping this, right? So a 5 on the bottom. So -4/5. The second term, 21 divided by the 7 is 3, and the 5 on the top gives me 5 on the bottom left, so I get 3/5. Those look alike, but they are not. The last two numbers are zeros. Next is 0, 0, 0, -1, and last is 0, 0, 0. I'm sorry, did it again? That guy's a 1. I sure did want that 1 to be in the back, but no. And there is your new orthonormal basis. Be very careful with your numbers. Don't do what I tried to do and cram it all in, write really big. You may even have to turn your paper sideways so that you can do these calculations horizontally. And when you're doing these problems on the test, make sure that you write plainly enough and show all of your work, because if all you do is write an answer and the answer is wrong, I have no work to check, so you don't get any partial credit, all right? If I can see your work and find a mistake, I made plenty of mistakes in the process here. Make sure that you work these over and over. Another thing that you can do to check it is to make sure that the magnitudes of each of these are 0, and make sure that the dot products of any of these with any others of these are 0. Now obviously the dot product of this one with any of the others and the dot product of that one with any of these will be 0 because of where the zeros are. But when you dot product this one with this one, what are you going to get? You're going to get -12/25, +12/25. Your dot product is 0. So you have established that this is an orthogonal set. And squaring it, adding together, taking the square root, you'll see that all of the magnitudes are 1. And that's how you know if you're in R4, you need to have 4 vectors. If you have 4 vectors in R4, then as long as they are orthogonal and normal, then you know that you have an orthonormal set that is a basis for all of R4. One last thing that wasn't on your syllabus is the cross product. This is from 5.3. It wasn't supposed to be included in this class, but it's very important for you when you get to Calc 3. And there are other times in other courses where you're going to do this and you may not understand exactly why. The cross product of any two vectors, we're talking in three-dimensional real space here, is going to give you a third vector that is orthogonal to both of the vectors that you started with. If you make a peace sign, stick up your first 2 fingers in a V. Any 2 vectors, look at your fingers, any 2 vectors create a plane. Do you see the plane that your 2 fingers make? Now you can move your hand however you want through space. Those 2 vectors are always going to lie on a plane. Now take your pencil and stick your pencil between your 2 fingers. Make sure it's straight, right? Those 2 fingers create a plane, and your pencil, if you keep it straight, you know what I mean, is an orthogonal vector to those other 2 vectors. One end of your pencil will be U cross V. Where it sticks out the other side is V cross U. All right. Now, cross product is just the determinant of a 3 by 3 matrix. And you've got two vectors here, then an IJK component and an IJK component. So the top row of your matrix, you're going to write IJK. You're going to put the components of the other two vectors, make sure that they are in order because cross products are not commutative. All right. So expanding about row 1, the first one's plus, then a minus, then a plus. You're going to isolate the I and the J and the K, cross out the I column and row. You're left with that minor right there, U2, U3, V2, V3. Find that determinant, and you've got your cross product. So let me finish writing this out. You're going to have U2, V3 minus V2, U3 in the I direction, and you don't have to write this down. It's completely simple when you have numbers. Just be careful with your signs. Minus U1, V3 minus V1, U3. You may run into this in a different class where it's written out the way that I'm writing it right now, and they won't tell you that you're just taking the cross product. So now that you've seen it, you'll recognize it, and you'll understand that this awfulness right here, if that's all they show you, is just a very simple cross product, U cross V. Now, if we did it the other way and we had V cross U, we would have to have the V here and the U here, and we would end up with the opposite of our answer. Okay, again, just some notes for you to have. Any two vectors in we're only talking about three-dimensional space, but in any vector space, any two vectors will form a plane. Okay, the cross product of those vectors, and now we're talking about R3, the cross product always yields a vector that's orthogonal to the original vectors. And this is very useful, especially when you take that orthogonal vector and you normalize it. Especially those of you who are going into engineering, you may have a surface and you can find two vectors on that surface at a particular point that are tangent, the plane that's tangent to that surface, and you find the cross product, and you can get a vector that's that's orthogonal to that surface, and it's very useful when you're talking about forces. Okay, some properties of cross products. It is not commutative. You end up with the other direction vector. Remember, there are always two vectors that are orthogonal to a plane. One goes this way and the other one goes that way, and they're simply opposites of each other. Cross product is distributive. If you're adding two vectors and you want to cross another vector with that sum, you can add the two cross products. I don't know why you'd want to. Seems like a lot more work, but it is true. Scalar multiple of a cross product, don't multiply both of these because then you'll have c squared times it. You can multiply the first or you can multiply the second before you do the cross product, but do not. This is useful to know if some of your vectors have nasty denominators. You can factor out the denominator, and then you'll have whole numbers in your vector. And it's easier to find that cross product with the whole numbers. So just a pointer. If your vectors have been normalized and they're all over the square root of 13 or 17 or something, you might want to factor that out and then do the cross product first. Okay, when you cross any vector with a zero vector, you get the zero vector. That makes sense, right? Because one of those rows in your matrix are going to be all zeros. If you cross a vector with itself, you're going to get the zero vector. All right, let me say that again. You cross a vector with itself, you get 0. Anytime you cross parallel vectors, you get 0. Because if two vectors are parallel to each other, there's one is just a scalar multiple of the other, and you have this situation right here. You're crossing a vector with itself if they're parallel after you've pulled out the scalar multiple, and the cross product is 0. Okay? Now, this guy here on the bottom is useful when you get to Calc 3. It's called the triple scalar product. Why is it a scalar? Because you're going to do the cross product first. Order of operations says go in the parentheses, and then you're going to find a dot product after that. Now, when you find the triple scalar, you can do this in one step, because instead of having the ijk, you can put u. Okay, look up here. If this was another vector dotted with this cross, then you would take the x component times the x component, the j component times the j component, and the k times the k. So if you just replace these with u, you just do the determinant and you've done the triple scalar product. Very cool business. All right, that's very useful, like I said, for other things. Now, one example of finding a cross product, and this is just the vector 2, 3, minus 1, and this is minus 1, 1, 0, right? I wrote it that way just so you could see the ijk. So if we're doing u cross v, u goes in front of or above the v. You've got your I component, j, and k. You're going to use this form right here. You can also use the shadowing, but then you'll have to go back through your answer, group your i's and j's and k's, because they're going to be all mixed up. So this is actually easier to do it this way with your minors and cofactors. So the minors for I is this little matrix here, 3, minus 1, 1, 0. J is in the minus spot, so minus j times this, marking out that column and that row. You got a 2, minus 1, and a minus 1, 0. And then the k, boom, boom, is in the plus place. You get this little minor right here. Do your determinants. 0 minus a negative 1 gives me 1 in the I direction. 0 minus 1, but you're subtracting, which makes that plus. And then 2 minus a negative 3 gives me plus 3, and I get a 5. Now that is your cross product. What I want you to do is take the dot product of this with each of these and prove to yourself that they are orthogonal. If they're orthogonal, your dot product has to equal 0. So check that out and have fun with your homework. Just a few problems from section 5.5. Seven through 13, every other odd. It's just a few problems, and this is section 5.5.